Now let's look at the force generated by magnetic field and the force experienced by a current element in an external magnetic field. Okay, external magnetic field means that this magnetic field is not produced by this current. Okay, this is the external, okay, magnetic field. Okay, so in order to calculate this one, okay, the force, okay, which is experienced, okay, by a small segment dq of a charge moving with velocity u is given by this one. So we have learned that when there is a charge moving in an environment that has the magnetic field, the equation used to calculate the force experienced by the charge is equals to F is equals to Q multiply U and cross product with the B. So when the current flow in a line, okay, there are electrons that is actually moving inside the lines. Okay, so the differential force, okay, on a small segment, okay, a very small section of the line is represented by this one, and the velocity, okay, can be rewrite as this one. Okay, so the whole equation here can be rewrite as these equations. Okay, now we can rewrite this equation by changing the differentiate, okay, to become integration here. So the total force on any closed loop, okay, sorry, the total force, okay, experienced by the current field element, okay, in an external field can be obtained by integrate the current, okay, with its length and cross product with the magnetic field. The total force on any closed current loop in a uniform magnetic field will be 0 because the integrals of the displacement vector dl over a closed contour is 0. So when we perform this integration, okay, it will give us the answer of 0. So if you want to find the force experienced by a closed loop current, okay, it will be equals to 0. So let's look at an example. Imagine this is there is no current here, okay, no current here, and of course there will be no force. Okay, when the current is flow in the z directions, okay, and the direction of the magnetic field is in the x directions, okay, is in the negative x direction, sorry. So the direction of the force will be negative y. This is the cross product between the I and also the B. Okay, we will get a force, okay, which is acting in the negative y direction. That's why you see the current is bent in this way. And when the current flow in these directions, okay, which is the negative z direction, and the magnetic field is in the negative x directions, we will get a force which is pointing, okay, in the positive y direction. That's why you see a curve here. Okay, we will look at the example on how to use this equation in order to find the force experienced by a current filament. So I have a finite current element oriented from at 0, 0 and stop at the origin. Okay, it carries 5 ampere in the x direction, okay, in the negative x direction. This current element is exposed to magnetic field flux density, magnetic field flux density B equal to 5 unit vector z Tesla. So for the force which is experienced by this current element, okay, and sketch a diagram to show the direction of the force. So we can look at the solution. So you have a current filament from at 0, 0 pointing to the origin. So the current is flow in the negative x directions and B is in the positive z direction. Okay, your I is equivalent to 5 ampere. So if I draw this thing, okay, in 2D diagram, okay, 2D diagram, this one will be the current filament and the magnetic field, they are in the positive z direction. So we have to apply this one, okay, this equation to find the force. So I is equals to 5 and dl represent the length of the current filament. Okay, so the length of the current filament is depend on the value of x. So the dl will become dx. Okay, the direction of the L will follow the direction of the current flow, which is in the negative x directions, and the cross product with 5 unit vector z directions, and the length, okay, of the current filament is 8, right? 8 unit. So you integrate from 0 up to 8 unit. Okay, you can also change this thing. Okay, if you want to follow the direction of the current, okay, by specifying it in the interval, it will be from 8 to 0. But for this one, okay, you have to change it to x instead of negative x. So you can choose either one. Okay, so if I continue with this one, I will get 25, and my direction will be negative y here. Okay, and when I perform the integration, I will get 200 Newton, and in the y directions. Okay, in the y direction. So this is the first questions. So the as current will experience a force in the y direction. You can draw it out. Okay, so this one will be a exercise for you. Okay, in the assessment, you can try it later on. Very similar to the first questions. And this one, okay, I want you to do it as your individual activity. Later I will specify in individual activities.